at the top. Ultimately, you want to be able to simplify expressions that are either in exponential or radical form. And it says all of the properties of powers you learned in lesson 5.1 to apply rational exponents will still apply. Or it says apply to rational exponents. So that's knowing when do you add exponents, when do you subtract exponents, when do you multiply exponents. We reviewed yesterday how to make a negative exponent positive. So it's all of those properties that would still apply if you have a rational exponent. So we can still use those. And then it does say to write all expressions with positive exponents. So make sure in your answer all exponents are positive. And then it says any exponents in the denominator of a fraction must be positive integers. So you may not leave as a final answer an exponent in the denominator that is a fraction. All exponents in the denominator need to be positive integers, meaning they would be whole numbers. So then it says it may be necessary to rationalize the denominator. So if we look at example 1, it says simplify each expression. And so this is reviewing, like I said, properties of exponents. It's also reviewing how you work with fractions. So for A, if we have p to the 1/4 times p to the 9/4, when we multiply those two terms together, what can we do with their exponents? We can add the exponents. So this would be p to the power of 1/4 plus 9/4. Now, this example is nice because your denominators are the same, but remember, in order to add or subtract fractions, you need a common denominator. So if you were to not have one, you would have to get one. So this would be p to the 10/4. Add the numerators, keep the denominator 4. And then make sure in your exponent then, any fractions are simplified. 10/4 can simplify to 5/2. So this is p to the 5/2. And you might have questions as we move through examples. In general, if a problem is given to you with rational exponents or in exponential form, you should leave your answer in exponential form. If a problem is given to you in radical form, you should leave your answer in radical form. So even if you're switching between exponents and radicals, your answer should be in the form that the original problem was given in. So I'll talk more about that as we move forward with examples. For part B, we have r to the negative 4/5. So I know it's small print, but that exponent is negative. So how did we say yesterday that we make an exponent positive? How do you make an exponent positive? Not multiply by the reciprocal, but just take the reciprocal. You just flip it. So it would be 1 over r and then to the positive 4/5. So by moving it to the denominator or taking the reciprocal, you are then changing the exponent to be positive. Now, up above when it said any exponents in the denominator of a fraction must be positive integers, that applies to this example. Because right now, the exponent in the denominator is positive, but it is a fraction. It is not an integer. So I want you to understand why we have to rationalize the denominator in this case. If you remember from yesterday, r to the 4/5 means the 5th root of r to the 4th power. So having a rational exponent in the denominator is the same as having a radical in the denominator. And we've already talked about how you can't leave a radical in the denominator. You need to rationalize the denominator so that the radical is out of the denominator. So whether you still keep this and work with it in exponential form or you rewrite it as a radical to work with it, that doesn't matter to me. Your final answer, though, should be in exponential form since the problem was given in exponential form. So I'm going to keep working with the exponential form. I just wrote this so you understood why we have to rationalize. So to rationalize, we have to multiply by some quantity so that the r in the denominator has a positive integer exponent or a whole number exponent. So I'm going to be multiplying by r to a power. So if I have 4/5 and I know when I multiply exponents I add, or multiply powers I add the exponents, what would I have to add to 4/5 to make it a whole number? 1/5. So I'm going to multiply by r to the 1/5, and then I multiply by the same thing on the top. Bless you. So on the top, I have 1 times r to the 1/5, so I have r to the 1/5 over on the bottom, r to the 4/5 times r to the 1/5 becomes r to the 5/5, which 5/5 is just 1. So it's r to the 1/5 over r. And if you had r to the first, that's fine. This then is simplified. All exponents in the problem are positive, and even though I have a rational exponent on the top of the fraction, that's okay. In the denominator, my exponent is an integer. So this is why you have to rationalize. Grace?
What is that?
This? I wanted to show you these are equivalent. This is the radical form of r to the 4/5. So I was showing you why you have to rationalize. If you have a rational exponent in the denominator, it means you have a radical. So that's why we had to do that process. And if it helped you to switch it into radical form to then rationalize like we were doing before, you could do that. All right, so I would like you to do examples C and D. So simplify those two expressions.
I don't get why. I don't know how. My answer actually. Okay, now give me it for a second.
All right, I think we're all good. Just double check. C is y to the 5/7. You just add the exponents. And then for D, you take the reciprocal, make the exponent positive, rationalize the denominator. All right, so then moving on. So I need your attention back up here, please. So here I have two examples on this side, one on the other, just additional examples of simplifying expressions. And as it says above this, and we'll see this applied to at least one of our examples here, when you simplify a radical expression, you always want to use the least index possible. So what I mean by that is, for example, if you look at B, it's given to us as a 6th root, and that might not be the least index possible. We might be able to change it so that it's a cube root or a square root, so a lower index. And so it says using rational exponents can make this process easier, but your answer, if your problems are given as radicals, your answers should still be given as a radical, in radical form. So that's what I was saying before. If you're changing to exponents in a problem, but it's given as radicals, you should change it back to radicals for your answer. So we're going to look at example A first. These take, I guess, a little more thought to simplify. So we have the 4th root of 32 over the cube root of 2. Now, one thing I want to say, it doesn't apply to this example. If these, if both of the indexes were the same, you would be allowed to divide these. So if these were both 4th roots or both cube roots, we could divide 32 and 2. So I know we can't do that here, but I do want to point that out. That happens in some examples where if these were both the same index, you could divide, and that makes your simplifying a little bit easier. So as it is right now, what I'm going to do is I'm going to rewrite both of these radicals in exponential form. So I'm going to write the 4th root of 32 as 32 to the 1/4 over the cube root of 2 is 2 to the 1/3. So I'm going to write them both in exponential form. And then what I want to try to do is these bases, the 32 and the 2, I want to try to get the same base. So thinking ahead as to why I would want to do that if possible, if my bases were the same, say they were both x, then when I'm dividing I can subtract the exponents, but if the bases are different, I can't do anything with it. So because I have a base of 32 and a base of 2, what I want to think about is, can I change the 32 so that it is possibly 2 to a power. So is there 2 to some power that equals 32? 5, yes. So 32, I'm just going to make a note up here, 32 is 2 to the 5th power. Okay, so I'm going to rewrite this. I'm going to here just put parentheses around the 32. So I'm going to have in parentheses, I'm replacing 32 with 2 to the 5th, and that's still raised to the 1/4. And then I still have 2 to the 1/3 on the bottom. But now notice I have both bases as 2's. So what I'm going to do here now is I'm going to simplify on the top. I have a power to a power. So when you have a power to a power, what can you do with those exponents? Multiply. And 5 is like 5 over 1. When you multiply fractions, you multiply the top, multiply the bottom. So this is 2 to the 5/4 over 2 to the 1/3. And now, because both bases are 2's, I can subtract the exponents. So this becomes 2 to the power of 5/4 minus 1/3. Now, whether you are subtracting using a calculator, subtracting by hand, that doesn't matter to me. I just want to review with you by hand how to subtract fractions. I said before, when you add or subtract fractions, you need a common denominator. What's the common denominator for 4 and 3? 12. So I would have to multiply the 5/4, the top and the bottom, by 3, and the 1/3 I have to multiply top and bottom by 4. So 5/4 would become 15/12, minus 1/3 is 4/12. And then I can subtract the 15 minus 4, which is 11. So I get 2 to the 11/12 power. And this is then simplified. There isn't more I can do with this. However, again, my original problem was given in radical form, so I want this to also be in radical form. So I would then switch it back to a radical, and it would be the 12th root of 2 to the 11th power. And you could leave it like this, or if you wanted to actually calculate what 2 to the 11th power is, that would be fine, but this would be an acceptable simplified answer. So notice we took 2 radicals being divided. Our answer was 1 radical. It has a different index, but we're using properties of exponents to help us get there. So a lot of these examples, it takes some time, some practice, some thought, some problem solving, and how to manipulate the problem so that you can get to the most simplified answer. Was there a question? Up here? I multiplied the 5/4 by 3 over 3. So when you subtract fractions, you need a common denominator. So I needed both denominators to be 12. Okay, other questions before we move on? Pardon? Because when you're dividing powers that have the same base, you subtract their exponents. So we're simplifying this to 1 power, not dividing the 2. So it would be the same as if I had, say I had x to the 6th over x to the 4th. I can subtract these to just be x squared, but the x is still there. So the base stays, you're just subtracting the exponents. Grace? You should, if the original problem is given in radical form, you should write your answer as a radical. If now, say on a test, you got to here and you didn't rewrite it in this form, I would probably make that as a note on your test. Would I take off for that? No. Because if you made it to here, then you know how to simplify it. It's just if it's given as a radical, you should write it in that form for your answer. Okay, we're going to look at example B. So like I said, each of these three examples, they're a little bit different. So we have the sixth root of 4x to the fourth. And you might be looking at this to begin with and thinking of how we simplified radicals before, and you could say, okay, I can break this into the sixth root of 4, the sixth root of x to the fourth, but I don't have anything to the sixth power or higher, so nothing cancels out, so it should already be simplified. There is a way to simplify this in terms of making this index a smaller index. And we can use exponents to help with that. So if I have, well, first I'm going to break this apart. If I have, this means I have the sixth root of 4 and the sixth root of x to the fourth. And that means I can write each of these in exponential form. So the sixth root of 4 would be 4 to the 1/6, bless you. And then the sixth root of x to the fourth would be x to the 4/6. So hopefully you can already see that for the x, this 4/6 will simplify to 2/3. So that's already simplifying the index of the radical. The 4 still appears like it can't be simplified. However, here's where you again want to think like we did up here for the 32. We wrote it as a number to a power. Is there a number to a power that equals 4? 2 to the second. So I can replace the 4 with 2 squared, because then I'll be able to simplify my exponent. So I'm just replacing the 4 with 2 squared, and that's still being raised to the 1/6. I'm going to change the x for right now. The 4/6 would be 2/3. Okay, so then for the 2 squared raised to the 1/6, like we did up above, we can multiply those exponents, and that would be 2/6, which is 1/3. So this becomes 2 to the 1/3, and then I have x to the 2/3. And like I said, notice now both denominators are 3. That means we started with a sixth root, and now we have cube roots. So we made the index smaller by by simplifying these exponents. So now if I go back into radical form, because there's no other way I can simplify the 2, and then x is just x. So 2 to the 1/3 is the cube root of 2, and then x to the 2/3 is the cube root of x squared. And then because they are both cube roots, I can combine it into 1. It's the cube root of 2x squared. And that would be the simplified radical. So for this one, yes, everything, if you look at the original, look at the answer, everything is just divided by 2. That won't always happen though. That's kind of a coincidence for this one, but that's not the case for every single one. And in some cases, you might end up where your terms have a different index. One might be a fourth root and one's a cube root, in which case you can't actually combine them, but you want to make sure they're both simplified as much as possible. Okay, and then I have one last example to go through with you. This one is a little different yet. It says simplify the expression. And again, why do we need to simplify? So that you understand when you simplify or when you don't need to. We are simplifying because we have a rational exponent in the denominator. So you don't have to write this, but another way to write this expression in radical form versus with exponents, the 1/2 power means the square root. So I could write this as the square root of y plus 2 over the square root of y minus 2. These are equivalent expressions, And maybe then from when we worked with radicals, seeing this, you might understand a little better why we have to simplify it. There's a radical in the denominator. That's the issue. So I'm going to keep it. I'm going to work with it in exponential form, but I just want you to know you can switch it to radical form and then simplify like we did with radicals if that makes more sense. Just make sure you switch it back in the end. So in order to simplify this, I have to rationalize the denominator. So first of all, if I look at the equivalent radical form, what would I multiply this denominator by if I wanted to rationalize the denominator and cancel out the square root? Close, the square root of y plus 2, and that's called the what? We're multiplying by the, what does it see? Conjugate, yes. Okay, so then equivalently then up here, how if you kept it as an exponent, that means, again, I'm multiplying by the conjugate, so I would be multiplying by y to the 1/2 plus 2. And I have to multiply by that same thing on the top. But like I said, if the radical form makes more sense and you worked through the whole thing in radicals, that's fine. So then I have to FOIL on the top and the bottom. So when I multiply y to the 1/2 by y to the 1/2, I add the exponents. 1/2 plus 1/2 is just 1, or 2 halves. So y to the 1/2 times y to the 1/2 is just y. Y to the 1/2 times 2 would be plus 2y to the 1/2. And then for the inner terms, again, I have 2 times y to the 1/2, so plus 2y to the 1/2. And then I have 2 times 2, so plus 4. And when I simplify, I will be able to combine the middle terms. On the bottom, FOIL again, y to the 1/2 times y to the 1/2 is y. Outer terms, y to the 1/2 times 2 is plus 2y to the 1/2. Inner terms, negative 2 times y to the 1/2 is minus 2y to the 1/2. And then a negative 2 times 2 is minus 4. So on the bottom, and this should always happen with conjugates, notice the positive and negative 2y to the 1/2, they cancel each other out. Your rational exponents in the denominator are gone. And that should always happen, as long as you're multiplying by the right thing. So my denominator is now just y minus 4. I no longer have rational exponents. On the top, I just combine the middle terms, so I have y plus 4y to the 1/2 plus 4. And then I do want to make it clear, this is simplified. You cannot cancel out the y's. You cannot cancel out any of the 4's. This is in simplest form. Nothing cancels from top to bottom. And since I no longer have that 1/2 power in the denominator, it's simplified. Okay, questions on that one? Cora? Yeah, 1/2 plus 1/2 is just 1. Oh, when you're adding the like terms, you don't add the exponents. You're just adding the coefficients. You only add exponents if they are being multiplied. Okay, so then there is a summary at the end for expressions with rational exponents, what it means to be simplified. So make sure you have no negative exponents. Every exponent in a denominator is a positive integer. It's not a complex fraction. That means a fraction within a fraction. And any index is the least number possible. Now, what I had this thought in my mind,